So,
Yes.
okay, so it's my pleasure to introduce the second speaker for today, Denis Nardin, with a talk from University of Regensburg, with a talk entitled Equivariant Multiplicative Structures.
So, hello everyone. It's a pleasure to be here. I have to confess, I'm not quite sure what kind of background to give because I'm not a category theorist by trade. I do homotopy theory. So I might be saying stuff that is going to be completely obvious for all of you at the beginning. Not sure. Or I might say something, I might take for granted stuff that's absolutely not obvious. So please interrupt me if I am somehow screwing up with the background. So first, I should mention this is a joint work with Jay Shah of the University of Münster, and it's building up upon an older work that we did with Clark Barwick, Emanuele Dotto, Sol Glassman, and Jay Shah again. The problem of this work is somehow define what it means to take tensor products of a G set of objects, whereby, I should mention G here is going to be a finite group throughout this talk. The theory can be more general than that, but let me keep then the case of a finite group just for the sake of concreteness. And so the first question is, well, what does it even mean to give a G set of objects in your category? And well, I'll touch it later, but the problem in some sense is, you want to take a tensor product of a G set of objects and somehow not forget about the action. Okay. This is a problem that arises in questions in stable homotopy theory. Essentially, we are trying to capture what kind of categorical foundations you can give for stuff like the Hill-Hopkins-Ravenel norm, which is sort of a generalization of the Evans norm in group cohomology. But okay. So to do first, I will do a review of what it means to do non-equivariant multiplicative structures. So the question is, what does it mean to give for example, a symmetric modular category or so on and so forth? And I expect this to not be really new for most of the audience, but just for the sake of concreteness, let me give the definition. Symmetric multi-category, or as I'll call it more commonly an operad, is the datum of the following. So first a set of O of objects. Sometimes these are called colors, but this doesn't really matter. And 2, for any I finite set, and C underline an I family of objects, by which I mean just a map from I to the set of objects. And the object of C, I give what I call a multi-mapping space, C underline D. Well, a set. These will become spaces at some point when I will give the examples, but for now, let's keep it into sets. And then a composition map. For every F map of finite sets. say D, an object of C, let me say E, sorry, E, an object of C, the J family of objects of C, and C underline an I family of objects of C. So I give a composition map that works like that. Yeah, sorry, J. I'll explain in a second and I'll give some examples. So don't be too frightened. If the definition seems a bit obscure. Okay, a composition map like this that I guess I could call circle F, just for the sake of giving a name, that is associative, unital, natural, etc. I don't want to spell it out, but well, I'll give a more precise definition later. But okay, what does this mean? Well, essentially, I have a set of objects, which are, you can think of them as the objects of our symmetric model category, and then a set of maps from an object. So let me give an example. Let's take, for example, vect, be the operad, whose objects are vector spaces over F, a field, for example, and then mul I, let's say V underline PW is just a set of M maps from the product M multilinear. So that's what it means. These are maps that take input in a set of objects. Multilinear, I mean linear in each variable. Okay. And the composition is given by the obvious composition of bilinear maps. And the reason why I say that it's natural is, for example, that sigma I, which is just a set of bijections, should act on mul I CD. And if you try to spell, you can spell out the whole coherencies this needs to satisfy, but it's a bit long, and it's a lot easier to package it in a nicer form, which I will do now. So first, the first observation is that just for writing the composition, you notice that we have some kind of asymmetry here. Here we have just one set of objects, but here we have a product, sorry, a set of morphisms. Here we have a product of sets of morphisms. So for convenience sake, we just define for every F goes from I to J, and for every C, an I family of objects, and D, a J family of objects. We define mul F C underline, D underline is just a product of these sets of objects, DJ. So, okay, that's just a convenient notation. And now the composition can be written as for every pairs of composable arrows, you get a map. Sorry, let me write it like this. Okay. So the composition, let's say, I don't know, G, comma, F. These names won't be very important. So this suggests that there should be a category whose objects are families and whose morphisms are these multimorphisms. And in fact, we can do this. Turn page. So let's say O be an operad. Its category of operators is this tensor, I'm going to call it, whose is the category. It's a category. A tensor whose objects are pairs, where I is actually a finite, sorry, I plus is a finite pointed set. The importance of the pointing will appear in a second, but and C underline from I to O is just a I family of objects. And note that here there is no plus. There's nothing. That is, I'm discarding the base point when I am indexing the family. And then we decide that maps in O plus from C. So let's say, let me keep the finite set. Second, we define it as the disjoint union over all maps of finite pointed sets of this mu for F inverse J. C restricted to F inverse J, dj. And one can check that the composition defined above gives the structure of a category. Okay, and in fact this comes equipped with a functor to fin star, sending C underline I plus to just I plus. And the point is that this vibration here, which is not a Grothendieck vibration, I should mention, in general, recovers completely the operatic structure.
Excuse me.
Yes.
Hi. You said it is a vibration, but it's not a Grothendieck vibration.
Yeah, I'm a bit vague. Okay, I can give you exactly the properties.
If it's complicated, don't worry, it's fine.
No, it's not. I mean, it's actually, we're probably going to need it. So actually, let me spell it out exactly what properties they have.
Thank you.
So I'm calling it a vibration because it's vibration-like, but it's not literally a vibration. If anything, it's actually more like an up vibration, but I tend to call all of them vibrations. But okay, so as these three fundamental properties. So the property one, actually, to give the property, I need a definition. So a map F from I plus to J plus is inert if it's injective on F inverse J. That is, if you have a map of finite pointed sets, you can have, some points will end up to points of J, and some points will go sent to the base point. Say another one goes to the base point. And I don't care about injectivity, about you can send as many points to the base point as you want. Essentially, what this map is doing is taking a subset of I and throwing it all on the base point and isomorphically map everything else. And okay, so now the three properties. Let me call this P, actually. Properties that P has are, so, okay, for every F inert, and for every C in the fiber over I plus, so that's actually concretely an I family of objects of O, there exists co-Cartesian lift F tilde from C to lower shriek of C of F. So this is sort of like saying that it's a Grothendieck op vibration on inert arrows, but it's slightly stronger than that actually. Because being co-Cartesian in O tensor is stronger than being co-Cartesian only on the subcategory of inert arrows. The second is, okay, so for every I plus pointed finite set and little I in I, not the base point, there exists this map chi I, which is inert, which sending I to I and everything else to the base point. And so by property one, we have a push forward chi I lower shriek to O. And what this property is telling you is that this product of chi I lower shriek so this looks a bit confusing perhaps at first. So there's an equivalence. This is just telling you that an object over I plus is exactly an I family of objects of O. So. And it's actually telling you something more, but property 3 actually will imply this additional information. So we don't need it. And okay. And so for every F from I plus to J plus any arrow, and for every C underline object over I plus and the underline objects over J plus, so we can take this map F, C underline, D underline, which are just the set of maps lying above F. Let's just map. And we can take this and map it by post composition with the push forward. J of F, J, J, and you're asking this to be a bijection again. Okay, so these three properties are actually enough to recover the operatic structure, and everything that has these three properties is coming from an operad up to equivalence. Is this a satisfactory answer?
Yes, thank you. Thank you.
Okay, if this is not, if you're not familiar with this, you should keep in mind that this example, which is essentially the only example, and these three properties are just to guarantee that this comes from such an example. That sometimes is called an operatic fibration for more general basis. Okay. But okay, let me actually give, so we have our object here. Actually define, for example, a commutative algebra. Is a section of P tensor sending inert arrows to co-Cartesian arrows. So, okay. Concretely, what does it mean? It means by property 2, this, if you have, if you define, let me call it A0 for brevity, A of 1 plus, then this is telling you that I plus is the constant I family, A0, blah, 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 A0. That's the property of sending inert arrows to co-Cartesian arrows, because we have, right, we have I of I plus to O of little I. Remember, we have this. Okay, now let me not write an arrow here, but here there is an arrow, psi I, and this is lifting to an object AI plus, and this gets sent to a co-Cartesian arrow here. And property 2 tells us that this map is actually giving us the components of AI plus as an I family. So that's plus 1 plus. So this is just telling, yes?
Why do you call this commutative algebra? What should be an algebra?
Associative, you want maybe associative algebras?
I don't know, because you say commutative algebra, so I guess there should be some simpler notion going around.
Well, I don't know if I would call it simpler. The point is that the commutative operand is the terminal operand. I guess, but okay, there are other notions. Yes, I'm going to define what algebras in general are, but in a sense, this is simpler to define because this is the notion of algebra where you put all the possible constraints. And in some sense, this is more elementary than picking and choosing which constraints you want. I
understand. Okay.
Yeah.
Sorry, related question. This is because you take symmetric operands, right? Instead of just non-symmetric.
Yeah, you could do a version for non-symmetric things. Although this theory actually can recover the theory of non-symmetric operands. By just, okay, I'll explain more in a second, and then maybe I'll pass to the equivariant world. But okay, just let me show you where this algebra structure is coming from. Because, for example, we can consider this map M2 plus to 1 plus. That's just sending 2 points to 1 point and the base point to the base point. And then this gives us a map from A2 plus to A1 plus. And the point is, I didn't define a tensor product, but if there were a co-Cartesian push forward here, which in general there is not, this is what I want to call and the push forward along M is what I want to call the tensor product. So giving a map like this is the same thing as giving a map out of the push forward. And for example, the symmetry comes from the fact that this map M is symmetric. So I can pre-compose with the permutation that exchanges the 2 points of 2, and M stays the same. And this is telling you exactly that this multiplication is symmetric. And for example, the unit comes from the map U from 0 plus, which is just base point to 1 plus. This gives you a map from A0 plus to A1 plus. And if there were, and this is going to be the tensor unit. Sorry, plus goes inside. So actually you can recover the whole algebra structure out of this. And okay, what time is it? Okay. Let me say just a couple of words about what happens when you want to take different kind of algebras. So you have this configuration here, which is the category of operators. For example, if you want associative algebras, you can do the same thing, but instead of taking sections over thin star, you take sections over non-commutative finite sets, which is finite thin star is category with non-commutative, with objects, finite pointed sets, I plus, but then a map is a pair, a map of finite pointed sets, well, and a collection of things I'm going to call lesser or equal than J, where lesser or equal than J is a total order on the fiber for J and J. So this is telling me in which order I want to multiply. So while here I had an M, only one possible M map like this, in non-commutative sets, you get 2 possible M maps because they also need to give you an ordering of these 2 points to define the map. Okay. And you can do more clever things to get general kind of algebras here. And in fact, you can actually give the definition of an operad over thin star and C with the same 1, 2, 3 properties I wrote above, and you recover the notion of a non-commutative operad. Sorry, not non-commutative, non-symmetric operad. So on and so forth. So you can see in some sense this is more complicated because I have to remember more data in my operations. Okay. That's okay. This is a very old story, actually. I've maybe presented it in a slightly unorthodox way, but I claim no originality for this story. Let's go to a new page. Let's put equivariant objects. Before I go on, are there more questions about this? No. Okay. So, okay, this is, as I was saying, this is part of a work with Clark Barwick, Emanuele Dotto, Saul Glassman, and Jay Shah. So the intuition here, we want a notion of objects parameterized by subgroups of a group G. So for example, we should have a category CH for every H subgroup of G. And then for every inclusion of subgroups, we should have a restriction homomorphism. And for every subgroup and element in G, we should have a conjugation homomorphism. So I'll give the definition precisely, but let me first give examples. And for example, you can think of if you fix C on a normal. Sorry, let me put an underline actually here to distinguish. So if C is a category, C underline H could be what I like to call as functors from BH into C, which are just objects of C with an action of H, where BH is a category with one object and H morphisms. What I, perhaps with homotopy theory terminology, I would call the delooping of H. Okay, that's certainly an example to keep in mind, but we can have more. For example, you can have, if you have a C category, I can define C underline of H to be functors not from BH, but with something with a little more structure, OH into C, where OH is the category of transitive H sets. And this is very important because, okay, now I'm going to switch quickly to infinity categories for the example, but for example, if C is the infinity category of spaces, CH under this thing is the infinity category of H spaces. That is what you obtain by taking topological spaces with an action of H and inverting the maps that are equivariantly homotopy equivalences, which is not not actually what you obtain by the first examples. So that's an important example. And again, and again, you can define this A underline of H, AF, maybe I should put an F, being the span category of finite H sets. That's the Burnside category. Burnside category. That's another very important example. And then you can actually do something even crazier, and you take what I call underline G here, sorry. H is functors from this AF H into spectra, but I asked the functors to be product preserving. And this is the category, well, the infinity category of H spectra. So why am I giving all these examples? Well, because you might think that the only interesting example is the first one, objects with an action of H. But in fact, it turns out that it's sort of the least interesting example, although it's very good to keep in mind to keep the intuition. And in fact, this example is more interesting, and these two examples are a lot more interesting for the purposes, at least, of studying homotopy type of spaces with the action of a group. So actually, let me give the precise definition now. So that OG that I already mentioned is the category of transitive G sets. It's called the orbit category. Its objects are G sets of the form G mod H for some H. But note that H is determined only up to conjugation, so I'm not going to specify the H typically. So then a G category is a functor from OG up into cat. Or equivalently, Grothendieck up fibration C underline goes to OG up. In fact, we write the whole paper with the formalism of fibrations because, as you might or might not be aware of, it's a lot easier to construct fibrations than to construct functors into categories. But of course, the two amounts of data are equivalent. The two data are equivalent because we have the straightening and straightening equivalence that tells us the categories of these two different kinds of objects are equivalent. And you might also be surprised by my choosing the up fibration and not the fibration here, which would seem more natural, but it turns out to have a much better, in practice, it's a lot easier to work with Grothendieck up fibrations in this context. And the up on OG here is a small price to pay. Okay. So let me actually work out in detail how this works for an important example. So we can take thin G underline, which is just as before, this is sending an orbit G mod H to finite H sets. And this is not a definition though. As someone might have objected that this is not a sufficiently precise definition, so let me actually define the fibration here. This is unfortunately one case where defining the Grothendieck fibration would have been easier, but well, we have to pay our prices here. So objects are arrows. U goes to V, where V is in OG, is a transitive G sets. So these are arrows in finite G sets, which I decide to interpret as elements of this form for I finite H set. And morphisms are spans in this form. So these are morally, if I have, if U goes to V is of the form induced I goes to G mod H, and U prime goes to V prime is this. This is the same thing as G as a pair of G such that GH prime G inverse is contained in H, and a map from the restriction to H prime of I to I prime. You can actually unwrap what this means. And it means this. So this is in fact a fibration classified by the functor that I promised you, given the restriction and the obvious restriction and conjugation operators. Sorry, I should put a G. Okay. And maybe, let me copy these actually.
Sorry, up to this point, it was never important that G is a finite group, right?
No, in fact, the finiteness is going to be important only when I introduce monoidal structures.
Oh, could you stress it when it happens?
Yeah, but it's going to be quite obvious in a second when I introduce.
Okay.
But yeah, I will. It's already important here for if I would like to call about indexed coproducts, so coproducts taken by a finite G set, for example. But okay, I'll stress it more when it happens. Okay. And okay, as a variant, you can also take fin G star underline, which has the same objects, but more morphisms. I allow spans like these that I'm provisionally denoting as partial pullbacks, where partial pullbacks means just that U tilde goes to the pullback is injective. This in fact doesn't depend on the choice of the pullback, of course. So injective and not necessarily isomorphism. And this is because you can think of fin star as a category of spans with the left leg is injective. Okay, I think it's actually over with the previous work, and it's time to describe equivariant multiplication. Oh, yeah, okay. Now I can do it in this section. So, other questions so far? Okay, first thing is what is so let I a finite G set and C underline a G category. I'm going to define C underline of I, just the right-hand extension from the orbit category. So this is just a product for all the orbit of I of C underline of V. So morally, this is what I want to think of when I want to think of I families of objects of C. And for example, when C is what I didn't call, but okay, I probably should have called as Borel, so functors from BH into C. This is, what do I want to say? Oh, I want to say this CI is just functors from the action groupoid of I into C. It's my notation for the action of G on I. So essentially, for every i.e. for every I in I give an object Ci, but then for every G, I give an isomorphism Ci to CGI, and they're compatible. So this is something I could reasonably call an equivariant family of objects of C in this particular case. Okay, so the question is, what should be a G operand? And this is very much a question of finding the right definition. No, I have it here. So the step is, first we need for every a pre-sheaf of objects. So for every H, I have O of G mod H. And then the idea is for every F from U to V G orbit, I want a set mu F CD, where C underline is an ob O of U and D is an ob O of V. And actually, yeah. And actually, as before, we extend this to the case where V is not an orbit, just by taking the product of all orbits of V. And I want these to be sufficiently natural. So I'm going to write down the naturality condition, which before was just equivariance for the automorphisms of U, but here we need some kind of compatibility with the restrictions. And here it's going to be clear already what the issue is. Oh, actually, there was an issue before that needed G to be finite. Sorry, I didn't notice it, but okay. Let me first say here, and then it will be clear why it was needed also before. So this has to be natural in F, i.e., if I have a Cartesian square, I get a map. So let me put this is F, this is F prime, and this is, let's say, G prime. And okay, and claim that this already needs G to be a finite group to make sense. Why this? Well, because I am using that a pullback of finite G sets is a finite G set. That's already, or rather, I'm using that a G orbit is a finite G set. So, for example, a problem is if G is Z, G orbits. No, not Z. What was it? The one that didn't have. Oh, let's say Q. Yeah. G orbits are never. So there are no finite G sets. But it is true that this would work for any group if you allowed only finite G orbits. It's just the theory tends not to be, well, okay, I'm not going to say that. But sometimes the theory is just not interesting. Okay, but I should say this works as long as you restrict it to just finite G orbits. This works for any group G without any restriction. Am I saying this correctly? Yes, I think I'm saying it correctly. So I don't know if that's an
yeah, this answers my question. I mean, at least I'm okay. I don't know if it's important for other reasons, but this is enough.
I mean, the point is that these maps F that you want are telling you how many elements you want to multiply, and you just don't have enough examples if the fiber of F is not finite. And you can try to restrict in various ways so that the fibers of F are finite and that they're stable in their pullback. And one way of doing that is just restricting to finite orbits. Another one is to restrict only on G sets that have finite stabilizers. That's actually a more common restriction. Actually, I should say that's probably a more interesting example. But that you need to put some restrictions, and I'm just concentrating on the case of finite G sets because all those restrictions are automatic in that case. Because in general, right, you don't want a multi-multiplication for infinite families of objects. You just will never get examples of categories with this property. You want to somehow restrict to finite families of objects. How much time do I have, by the way?
So you started, I think you have around 5-10 minutes. Like,
okay.
Would that be enough?
Yeah. I'm just going to.
I mean, it's
actually,
10. If you need 5 extra, it's fine. It's no problem if you need 5 extra.
No. I just to decide what am I going to say. I want to give you at least a precise definition of what a G-operand is. So for now, I'm giving you the desiderata, and then I'm going to need a multiplication, which is natural, associative, and unital. But okay, you can actually spell it out exactly what it means, but I'm not going to. I'm just going to give you the fibration definition because it's a lot more compact and actually easier to work with. So G operand is a functor P from tensor to now you have finite G star underline. So this was this category I described before, where you have objects are maps from U to V, which you can think of them as pairs of H a subgroup and I plus a finite pointed H set, such that, wait, I forgot, I need to define what an inert morphism is. Okay. Let me first. So amorphism in thin star G underline, remember, was a span like this. This is kind of partial pullback things. Is inert if U tilde to U prime is an equivalence. And you can actually check that when G is trivial, this just recovers the notion of inert I gave you before. So this allows you to make the subgroup smaller and maybe throw away a few orbits, but nothing more. The orbits that you have after you restrict the subgroup, you have to keep. You cannot change them. You cannot collapse them, for example. So such that when you have co-Cartesian lifts over inert arrows, and 2, so for every map like this and W an orbit of U, you have this map, okay, W inside U, which correspond to those characteristic morphisms before, and you can verify as exercise that this is in fact an injection. It shouldn't be very surprising. It has a, in fact, it has a right inverse. Then the product of all overall W's of these maps from O to product of W of O, the identity of W. Let me just write identity W here. Is an equivalence. So this is telling you that the fiber over U goes to V is exactly U families of objects. And 3, as before, for every F you get this is a bijection or an equivalence if you're in infinity category length. And this is just copying the previous 3 conditions that I described. And you have maybe to play with it a little bit to convince yourself that this actually recovers this data that I gave you before. In particular, the push forward along, there are some push forward along inert maps that actually recover these restriction maps here. And okay, but I want to give you examples of this. And then I think I'm going to be over. Actually, no, I think I'm already over. Am I already over time?
You can give examples. That's fine. That's totally fine.
I can give you.
Yeah.
Just give you, and just give you a simple example where let's take C any category, symmetric model category. We can take C tensor Bohr, we call the Borel. G category is just perhaps not the most enlightening example, but objects are just pairs. So pairs C underline and U goes to V. This is in fin star G, and this is in this is just a U family of objects as before. So just a functor from UHG to C. And morphisms C UV to D U prime V prime. So I have to give you a morphism downstairs. And then let me give a name F to this particular morphism because this is going to be important. This is actually complicated to define precisely, but I'll try. So we have this map. So I can take C underline and restrict it to the action groupoid for this U tilde G. You have a map, equivariant map from U tilde to U, so you get a functor of action groupoids. And the idea is I'm going, no, what do I want to say? Oh, I want to say that I want to construct a functor from U tilde prime of G to C. And this sends little u to the product over U tilde in U tilde of C of f of U tilde. I'm taking a tensor product along the fibers. But then I need to tell you what it does on morphisms, and that it does sort of the obvious thing, but it's a bit tricky. So I'm going to call this C underline tensor F, and the other data is this, a natural transformation, actually, from this C underline tensor F into D. And yeah, okay, that's the example I want to give, but why do I care about this example? I care because this operatic structure survives after localization, sufficiently nice localization. So sometimes you can take the C bore and invert some kind of weak equivalences, and you get an interesting G operad. And that's exactly what happens if you take C orthogonal spectra and you take the stable equivalences of weak equivalences, and this way you recover the Hill-Hopkins-Ravenel norm with all its duty and coherences. Okay, I think I'm going to stop now.
All right, so thanks, Denis, for the very nice talk. And this is questions time. So whoever has something to ask, please do not hesitate to do so.
Yeah, I have a couple of questions.
Yeah.
So the presheaves on the effective Burnside category, this is the genuine equivariant theory, right?
Yes, product preserving presheaves.
Yes, right. I'm a bit, let's say, I never been much into equivariant theories, so I never really understood why the genuine equivariant G spectra, let's say, are so much more powerful and interesting than naive G spectra.
So
can you give like
there are two answers to this. The answer number one is that they're a very convenient bookkeeping tool. They actually allow you to take huge amount of data and package it only in one G spectrum. So for example, okay, this might or might not be very interesting for people, but you can rephrase concisely constructions and conjectures in terms of G spectra. So for example, i.e., for example, the Seagull conjecture can be rephrased as ng of x is Borel, where Borel, oh, actually, let me say co-free, maybe. That's an older terminology. I don't like it particularly, but I've already used Borel before, so by which it means that it's homotopy it's genuine fixed points correspond to the homotopy fixed points, or another way is you can package Hermitian K-theory and K-theory in an unique C2 spectrum, which we call real K-theory. So these are two reasons. This is one reason. You can actually find this G spectra in reality. Another way is that K-theory as the base varies through, I don't know, all the field extension of a given field, can be packaged all together as a one G spectrum where G is the Galois group. Mm-hmm. So they're very effective like packaging tools. You can actually put stuff there and and work with them in a neat way. And the other time is actually that spectra with G action, what I call Borel G spectra, actually embed inside G spectra, as those spectra for which the genuine fixed points coincide with the homotopy fixed points. Mm-hmm. And sometimes it's useful to decompose a Borel G spectrum in terms of genuine G spectra. So, for example, this is a classical example in Hill-Hopkins-Ravenel. They have a spectrum that came to them by chromatic homotopy theory, which is a Borel G spectrum. It's just, you know, a variant of Morava E theory with an action of a stabilizer. It's not very important, the details what it is, but it is. And you are really, really interested in computing its homotopy fixed points, because it was super important. And the way they do it, they filter it, but they don't filter it here. They filter it here, and the associated graded is not composed of Borel G spectra. It's composed of much simpler genuine G spectra that are called the slices. And then they study these slices and they prove the result for the original guy. So even if you're interested only in these things, these objects actually are a powerful tool and actually very well behaved.
I see. Thank you very much.
Are there other questions?
Well, in case I have another question, I don't know if it makes sense though. Let's say you see your operands as represented as trees. I mean, the operation are just the inputs and the outputs is kind of the root. You have an interpretation for let's say, a tree-like for G operands? I mean, to visualize it.
Presumably, I never had the courage to write it.
Okay.
But you can see actually this interpretation as vibrations as secretly trees. If you go on the case where the G is trivial, inside this thin star, you can see that you have like chains of composable morphisms. Mm-hmm. And if you draw them the way I was writing it as points and, you know,
right.
These are secretly trees.
Yes.
And this is the same going to be with finite G sets, only there is all sorts of decorations going on. So there's certainly a way of writing in terms of trees. I never dared to try to make it explicit. So, right. What the chains of composable morphisms are in these things. But you can definitely think of them as finite trees with a G action.
Right. So there should exist like a dendroidal theory.
It should, but I tried once for 10 minutes to come up with what this dendroidal category should be, and I decided very quickly that it was going to be
I guess it's complicated,
tricky to describe. But there is some work by Bonventre and Prieto which developed such a dendroidal theory. Actually, we don't know its equivalent to our theory, and we are deliberately leaving it ambiguous whether it's, I mean, we believe it is, but we also don't want too much to try to prove the equivalence, because combinatorically already what we do is very challenging. Trying to compare to the result looks beyond our skills, combinatorially speaking.
So if I may, I have a question. So you made it very clear how one needs to use this sort of operatic fibration or a weakened notion of usual Cartesian fibrations to encode all the coherencies and data in an ordinary infinity opera. And then when you move to G operats, it seems to me that somehow you don't need a notion of equivariant fibration, but rather you're just imposing.
No, we're changing the base.
Right. Yeah. You're just changing the base, but it doesn't seem that it requires a theory of equivariant fibrations.
No.
So I wonder if you can if you could expand a little bit on this, on the reason why, or why it's just all in the base, and then you can.
Well, okay. Ultimately, the thing that's making this what I call an equivariant theory is what's called the Elmendorf Theorem, that I actually hinted at before. That if you have C a sufficiently nice category, relative category, sorry, meaning a category with a notion of equivalences. And by sufficiently nice, I actually probably mean a simplicial, covariantly generated model category, blah, blah, blah. I don't want to go into the technical definitions. You can consider these I called objects with C action. And you want to invert the genuine weak equivalences, by which I mean maps that are weak equivalences on all fixed points. And this is what you would maybe consider it like equivariant things. And this turns out to be the same as pre-sheaves valid in C from the orbit category. Sorry, C with the weak equivalence inverted, of course. And actually here I have actually, to be a bit annoying, I mean actually the infinity category localization, otherwise the theorem is false, but okay. And so here it's essentially what's making this work. You can think of these as, in our case, we are applying it for C cat or sim cat. And here it's telling you essentially that working with equivariant data is not really a matter of bringing your group along as much as adding coherences given by your group. Also, what would be, for example, your notion of equivariant fibrations?
Well, I don't know. I mean, I would expect the fibers to admit a G action and these actions to be compatible and ruled by the fibration.
But this is essentially the same thing as a fibration over the Grothendieck construction, over what I call the action groupoid only. If you're acting on a category, it's not a groupoid anymore. But so,
can you just write that down, please? I think I got lost.
Okay. Let me give you an example. Okay, question, what is a category with a G action? Let me actually put this question to you. You might think, oh, it's just I give a functor for each element of the group and etc. So what you're saying is secretly is a functor from BG to cat. And here cat, I see it as a 2-1 category with. So that I did this function, and maybe you want me to call it a pseudo functor. So I'll never do that because I don't consider them qualitatively different from actual functors. But then we have the unstraightening equivalence. Yeah, I cannot write. And this is the same thing as some kind of fibration over BG, where objects, in this particular case, this can be written very explicitly. So C underline is objects are the same as objects of C, but then maps are, so a map is a pair, FG, X to Y is a pair of G in G, and say a map from G lower star X to Y. And then you use the functoriality of the action to define the composition. And so this is basically the same yoga, if you want. You don't want to expel out explicitly what these coherences are, because you get mad very quickly. What you want to construct fibrations where the coherences are built in, and maybe adding conditions to your fibrations to make sure that your compatibilities are. This is the yoga of the Grothendieck construction, if you want. And in general, defining such an object is a lot easier than defining such an object. Now, this is concrete enough that you can actually hope to write it down. But in general, the more you try to add, now suppose you want to add, I don't know, restriction functors I was doing before, and conjugation, and etc. This gets a lot more complicated than just giving you an op fibration to OG op. This is just a fragment of a G category, by the way, because BG sits inside OG op as the subcategory of free orbits.
Also, I think that possibly what's, in a sense, trivializing my question that I hadn't realized earlier is that BG has got just one object, so there's no issue of, like, there's no sort of difference between having multiple G actions on the fibers interacting all together and just having a global G action on the total category. So I think that's also maybe implicit in what you were saying. I just realized it now.
Yeah, I'm doing a slightly more general case here where I'm allowing my objects to be something different than just objects with a G action, of course, because I want to cover examples like the span category that I defined. Just, for example, in this category, a edge is not just objects of span fin with an H action. It's a different kind of thing. And these examples are important. These are, remember, these are spans in, this is span, this is span infinite G sets. And that's not objects in span fin with a G action. It's just not. So yeah, you want to capture these examples. So you have to allow more general basis than just BG. In this case, this of course adds to the complication of spelling out exactly what the data is. While with the fibration, you just enlarge the base and you're happy about it.
Okay, thanks for your answers. I want to thank both speakers again. So we'll have a silent applause for both of them. And so now that the question time is over, who wants can remain here for just informal chatting and so on. And thanks for participating. And we will keep you posted and we'll let you know as soon as possible once the December event has been planned. We will let you know all the details, speakers, schedule, and so on. So thanks.
Thank you so much for having me. I think I might have to run soon though, because my boss in the other room might want to talk to me. Right. Okay, let me end.